Okay, so welcome everyone to the first informal Astro seminar of the year. We have a lineup of some really great speakers, I think. I'm really excited about it. Without further ado, I will now introduce, I'm George. I'm one of the organizers. Giovanni is not here right now, but he'll be back soon. And so Chris Hamilton, one of the members here, will introduce our speaker.
Yeah, thanks very much. So our first Thursday speaker this fall semester is going to be Uddipan Banik. So Uddipan is a PhD student at Yale, working with Frank van den Bosch. He was previously an undergrad in India, in Kanpur. He works on collisionless gravitational systems primarily and on dark matter. And he has a tendency to dig deep into the dynamics of these systems, trying to understand key physical processes that are going on. And I was very keen to invite him because I think he's done some of the nicest work in galactic dynamics over the last few years, particularly with regard to dynamical friction. I think we're going to hear about some of that today. So, Uddipan, take it away.
Thank you, Chris, for that introduction. It's my pleasure to be presenting here at IS on the work that I did on my PhD on gravitational encounters and the dynamics of collisionless systems. So, gravitational encounters, as we all know, are ubiquitous in astrophysics. It happens all the time. Many different astrophysical processes, such as galaxy-galaxy mergers, capture of satellite galaxies in host galaxies, status disruption of satellite galaxies, binary black hole mergers as well. All of these things involve interaction between a subject and a perturber. It can be a galaxy or a star cluster or a dark matter halo being perturbed by another similar object or by a massive black hole. Depending on how the encounter frequency, the perturbation frequency compares to the intrinsic frequencies of the stars or these particles in the subject, we can have three different regimes of gravitational encounters: impulsive, adiabatic, and intermediate regimes. In the very outskirts of the subject, the stars move with frequencies much smaller than the perturbation frequency. And so we are in the impulsive limit. And in that limit, we can neglect the internal motion of the stars when we compute how much energy is being exchanged with the perturber and the stars. And the opposite extreme, we have the adiabatic limit. That is in the very central part of the subject. The stars are going to move with frequencies much faster than the perturbation frequency. And so what that causes is that leads to an adiabatic shielding of the stars from the perturbation. So on an average, your actions of the stars are going to remain nearly invariant. But in the intermediate regime, the frequency of perturbation is going to be comparable to the frequencies of the stars. And that's when you have a lot of resonances. And these resonant interactions between the perturber and the stars are going to be responsible for secular evolution and what is known as dynamical friction. So what gravitational perturbation does is that it basically changes the orbits of the stars in the subject and also the phases along these orbits. Okay. So there are two ways to look at the perturbation of self-gravitating systems due to gravitational perturbations. First, we do this Eulerian approach, which is basically we look at the distribution function, which is sort of the phase space density, the number of particles in each phase space element. Q is position, P is momentum. And if you look at the evolution of the phase space density under collisionless assumptions, so galaxies and dark matter halos are to a very good approximation collisionless, 2 Boydian complex time is huge. So under that assumption, your F does not change with time as you sit on a particular patch in phase space, and always yet under Hamiltonian dynamics, your distribution function is not going to evolve with time in absence of collisions. And in the Eulerian framework, you can write this as this basically del F del T plus the Poisson bracket of F, the distribution function with the Hamiltonian of the system is going to be 0. So that's like the conservation of phase space density under collisionless dynamics. Now, in absence of any perturbation, your Hamiltonian is time independent, and therefore F will also be time independent, and your F, Poisson bracket of F with Hamiltonian is 0, which basically means that your F is a function of Hamiltonian, and therefore F is a function of the quantities of the system or the actions. But if you introduce a potential perturbation, an external perturbation, then your Hamiltonian is perturbed, by a time-dependent potential. And what that does is that introduces a perturbation in the distribution function. Your f is now going to take with time, your x is a function of time, the f is a function of time. And assuming that the perturbation is weak, we can do a perturbative series expansion of f in some small parameter. The small parameter is basically the ratio of the mass of the host galaxy. Then you can write f as f0 plus f1, where f1 is the linear order perturbation. If the perturbation is weak, we can forget about the higher order terms here, and we can linearize the collisionless Boltzmann equation. And that gives us a linearized CVE, which is the time evolution equation for the linear response of the system f1, which depends on the perturbed potential by P, and the unperturbed galaxy, that is the distribution function, the unperturbed distribution function, and the unperturbed Hamiltonian function. So that is basically how we calculate this response of the system to some external perturbation. Now we can also do a complementary approach. We can adopt a Lagrangian approach where we basically go to each star and ask the question, how do the orbital elements of the star, the position, velocity, and or action angle variables, those are going to change with time if you have some external perturbation. In the impulsive limit, since the perturbation is happening very fast, there's not much time for the stars to move, although they get some velocity kicks. From Newton's second law, basically get that delta V is equal to the time integration of the perturbing force. But the positions are not going to change much. So this is the impulse approximation. In the adiabatic limit, and the perturbation is happening very slowly, then your actions are going to be invariant. The actions are given by basically this thing, the line integral of position of the momentum, generalized momentum of the GRI, where RI is the position. And the angles, the corresponding angles, are just going to evolve linearly with time. So the actions are invariant in the adiabatic limit, away from resonances, however. There's a subtlety there. Because if you have resonances, by which I mean that the frequencies of the stars, in 3D, there are three frequencies, omega 1, omega 2, and omega 3. Those are going to be commensurate with the perturbation frequency, omega p. So here I've just assumed the simple case of a perturber moving in a circular orbit with circular frequency omega p. Then when this condition is satisfied, then basically the stars are going to be in sync with the perturbation all the time. And those stars are going to be perturbed a lot, and their actions are actually going to change. But what we can do is that we can always do a canonical transformation from the original action angle variables to what are called slow action and fast action, and slow angle and fast angle variables. Now, as the name suggests, the slow angle and slow action evolve slowly. But how slowly, that basically depends on this particular resonance condition. The slow angle is the time integral of this resonant frequency, and it's given by this. The corresponding action is going to be, in this particular case, it's proportional to IT, because the perturbation frequency is the third dimension. So the slow action and the slow angle are going to evolve very slowly, and they are going to basically undergo huge perturbations because of this external perturbation. And they are going to have long vibration time scale. But the fast actions, those are not going to change, and the corresponding fast angles are going to evolve at the unperturbed frequencies. So basically, adiabatic invariance of actions, therefore, is partially broken. Meaning the resonances, only one of the actions is going to change, the slow action in this case, but the fast actions are not going to change with that. So they are still adiabatically invariant. The slow action is going to change. So first I'm going to look at the impulsive limit. That is, if you have a very perturber moving very fast, such as a flyby encounter of a galaxy with another galaxy, and the relative velocity is much larger than, let's say, the internal velocity dispersion of the galaxy, then you're in impulsive limit. And then you can just compute the velocity changes of each star by this perturbing force without accounting for the change in the positions of the stars. So that's the impulse approximation. Now, to look at the validity of this impulse approximation, I've done this numerical experiment where we do an embodied simulation of two galaxies with harmonic profiles colliding with each other. And this is a very penetrating encounter with an impact parameter which is almost comparable to the size of each of the galaxies. The left panel is low velocity, the right panel is high velocity. And as you can see here, that low velocity encounter does a lot of damage to the system. It gives very large velocity kicks to the stars, and many of the stars get unwound, they're lost, and you're left with a remnant of bound stars. And that's because in the very central part of the subject, as I was talking about, you're in the adiabatic limit, so you're shielded from the perturbation. And your stars are moving very, very fast, so their orbits are not going to change much, and they don't get a lot of velocity kick. Most of the stars in the outskirts are, however, going to get velocity kicks, and some of them can exceed their escape velocity, and those are going to be stripped.
The two galaxies look like they're initially identical, so why is the final product not symmetric?
Is it just that you're showing?
No, it's there are some blue particles here as well. So it is actually, it's not covered by
red is always on top of blue.
Yeah,
Oh.
I'm sorry. Yeah, that's a high thing. So yeah, there will be particle exchange between the two galaxies. There are some red particles here in the center and some blue particles here in the center as well. Sorry for that. So yes, so basically you have these encounter. In the fast case, you don't do a lot of damage. These two galaxies basically pass right through each other without doing anything. And that's kind of counterintuitive because you would think that, you know, you hit something very fast and you will get a lot of damage, but that's not the case because the faster you go, the less time there is for the perturbation to happen, and therefore you do not get a lot of velocity kicks in the fast encounter case. Right. So this is kind of a busy plot, but I'm just going to draw your attention to these points here. These are the simulation results. Here I'm plotting the stripped mass fraction. How many stars are going to be stripped as a function of the velocity of the encounter divided by the internal velocity dispersion. We are in the impulsive limit here because the VP exceeds sigma. And the different lines, I'm just going to draw your attention to the green line here because that is that does not assume this what is called the distant tide approximation. So on top of the impulse approximation, you also assume, usually you also assume that the impact parameter is very large. So your perturber is moving very far from the subject. So that that's a standard computation. But what we did is that we did not assume that. We did this calculation for any impact parameter, and that's the green line. What we do is that we do kind of a semi-analytical thing. So we, instead of running a simulation, which we did, but we still wanted to compute the stripped mass fraction as fast as possible. So we did a Monte Carlo sampling of around 1 million particles from this distribution function of the Hartwig sphere of the galaxy. And we computed for each star what is the impulsive delta E under the impulse approximation, what is the energy change of each star as a function of impact parameter and velocity. And then if that delta E exceeds the energy, the mod of the energy of the star, then that's going to escape the system. And that's how we basically compute the stripped mass fraction semi-analytically. And you can see here that this response, this is like the response of the system, how many stars are going to strip, that goes as a parallel velocity. That's because in the impulse approximation case, your delta V, the velocity kick to each star is going to go as 1 over Vp. And I'm going to come back to this getting later on.
Modern sort of structural formation simulations have enough resolution to also lie along this green line? Do they agree with this?
I think they don't. I am aware of a lot of mass loss, like many of these structural formation simulations. For example, there's this case of artificial disruptions of relation simulation. And I think you overestimate the mass loss in many of the simulations. And that's probably because of softening and all these issues. Or you do not have enough resolution to cover the dynamics. But I haven't checked that. That's a good where do they lie in this stack? Right.
Sorry, I'm a bit confused. You're saying the green line is general for all B.
Yes.
And what's the red line? It's
right.
for large B, but
yes.
why it's not overlapping with the general?
Why it's not overlapping with the large B case? Yeah.
Because you say the green one is for all B.
Yes.
What's the difference between green one and
that's okay. So basically, you have a galaxy like that. This is the impact parameter, right? And it's moving with the velocity Vp relative to this galaxy. And if you assume that B is large, then what you can do is that you can calculate the velocity change in each star delta V, which, if this is Z and this is perpendicular direction is X, this is Y, let's say, delta V will go as, I don't know if it's visible from that side, but basically something like this. Can you see?
Yeah.
Yeah. Okay. And what you now do in if B is much larger than RS, let's say, RS is the typical size scale radius of this galaxy, then you assume you do a tidal expansion. There is an impulse. Yeah. So this basically goes as x squared plus b minus y whole squared. This is for a point. If this is a Plummer sphere, let's say, then this that. And you do this expansion of this by assuming b is much smaller than y, or b is much larger than y, because you look at the velocity kicks given to the stars here, and since b is much large, you can do this approximation and you can expand this. And so ultimately your delta V is going to be proportional X and Y and all these things. And what happens in the distant tide approximation is that usually, so the Harnquist sphere, for example, it's infinitely extended. There are going to be stars here as well. And the distant tide approximation fails to properly compute delta V for this large X and Y, because when X and Y are large, B is nearly equal to 1. So, and this distant approximation fails. So the red line actually overestimates the velocity kicks given to the particles in the very outskirts of the sun, where impact parameter is not large. That's why you.
So then when B is very large, then the green one is still valid, or the red one?
The green line.
Okay.
Green line is always valid. Yeah. The distant tide approximation, you would think that it works in the large B limit, but that works only when the subject is truncated and it does not extend out to infinity. If it does, then the distant tide approximation will always fail for some stars. That's why the red line is worse than the green line. Yeah.
Thanks.
Okay. Any other question?
These results are for Harnquist profile?
Yes.
But then, like for dark matter, like NFW.
That's right. Yeah, we tried to do this with NFW as well. We did it. You get very similar results, but the Harnquist has an analytic distribution function, and it's easy to just sample particles from that distribution function. For the NFW, you have to compute it by something called an Eddington inversion, and it's doable. Yeah, we did this for NFW as well. I'm just showing the results for Harnquist. It doesn't make much difference. Mass loss is insensitive to the outer slope of the density group. Because both go as R to the -1 in the center. So that's okay. Right. So after giving a brief review of impulsive encounters, I will talk about all these 3 different regimes of gravitational encounters in the context of disk galaxies and how they're being perturbed by different kinds of perturbation. I'm only going to focus on satellite galaxies impacting the disk at a certain angle with a certain velocity. But you can also do this for bars or spiral arms, any kind of perturbation, and look at how the disk is going to respond to any. And I'm going to discuss this in the context of something very interesting about phase-space spirals, which have been observed by Gaia. It's a very cool non-equilibrium feature of the disk galaxy that has been found in our Milky Way disk. So the disk is a low entropy system. It's highly ordered. There is ordered motion, unlike a spherical galaxy where stuff is just going around at random velocities. The disk has motion. So whenever you perturb the disk actually responds very, very much. Unlike a spherical galaxy, it responds a lot. And you get all these various different kinds of modes of oscillation of the disk. And here I'm just giving you a broad classification of these modes, that you have a planar mode, that there are no vertical oscillations. This mode basically only consists of alternate compressions and rarefactions of the stars along the plane of the disk. But there can also be transverse modes. It can be a bending mode or a breathing mode. In a bending mode, you basically have an antisymmetric perturbation. So that causes an antisymmetric response of the stars. So it's basically at one point in the disk, they will go up, and the next neighboring point, they're going to go down. So it's like that. So that's why it's called a bending. It's bending the disk. And warp, the Milky Way's warp is basically a bending mode. It's a very long wavelength bending mode. And the breathing mode is a symmetric perturbation. So at one particular point in the disk, the stars are going to go like that. So it's a symmetric perturbation. Right. Now, why are we interested in these different oscillation modes of the disk? That's because of this wonderful thing called Gaia, which is being able to look at all these various non-equilibrium features of our galaxy in very great detail. It has been known for many years that the Milky Way has spiral arms, it has bar, it has the warp. So people have known that, yeah, the Milky Way is not in perfect equilibrium. There are things which are out of equilibrium. But Gaia has actually shown us that even locally, if you look at just the solar neighborhood and you plot the vertical phase space of VZ versus Z of stars, then now you would expect that they should be just uniform. There should not be any pattern. But Untitled et al. 2018 paper showed that from Gaia DR2 data, when you plot this, you find that there is this very interesting spiral feature in this VZ versus Z space. And this, I'm going to talk about this later, but this basically comes from some kind of perturbation that hit the disk. And now the stars are now oscillating at different frequencies because the Milky Way potential is not a simple harmonic oscillator. The stars are going to move at different frequencies. And therefore you have phase mixing. And that's why you get this spiral feature. And simulations also show that we can get phase spirals from, for example, the merger of Milky Way and Sagittarius. The Sagittarius goes to the disk, it drives the stars out of equilibrium, and now when they phase mix because of different frequencies, you get this phase spiral.
So in contrast to most situations in astronomy, here the data looks better than the simulation. Is there an obvious reason why?
Right.
They're not plotting the same thing, but that's delta rho.
Yeah.
Nevertheless, one's a much cleaner spiral than the other one.
I think that's because you're focusing in the data, you're just focusing in the solar neighborhood, but in the simulation, you're focusing on the entire galaxy.
Yeah.
And therefore, you have worse resolution in simulation. I think that's one. So the phase space spiral is cool. It has a lot of information about the potential of the Milky Way, about the frequencies of oscillation on the stars. And therefore, we can do Galaxy cosmology. We can basically constrain the dynamical history of the Milky Way. We can start to think about constraining the Milky Way potential, talk about the distribution, for example, maybe. So I'm going to talk about that a little bit. Right. So how do we get a phase spiral? Let's just focus on one particular point in the disk and give an impulsive perturbation, vertical velocity impulse to all the stars in this particular patch. And what that does is that initially it creates this dipole perturbation in the phase space distribution function. This is VZ versus Z. And for all Z, you get a positive delta VZ. So you create a dipole. And now when the stars are going to move with frequencies corresponding to the potential of the Milky Way. Well, this is done for an isothermal slab. So this is not Milky Way potential. This is very simple illustrative plot. But the stars move with different frequencies for different actions. The ones near the center of this plot have smaller actions, so they move with larger frequencies. And the ones in the very far from the center are going to move with smaller frequencies because they have large actions. So you basically wrap up this initial dipole into a one-arm phase spiral or a bending mode, which is asymmetric. But for a breathing mode, you have a symmetric perturbation. So for all, for positive delta Z, you have a positive delta BZ. These stars are going to move up, and these stars are going to move down. So for negative delta Z, you have negative delta BZ. And therefore, you create a quadrupole rather than a dipole. This is an n equals 2 mode. And so you get a 2-arm phase spiral. If you go to higher and higher order modes, you will get higher and higher number of arms for the phase spiral. But these two modes are the most dominant usually. That's what you find the higher order modes are going to be best.
Is that a self-gravitating result? Or is that
no? This is pure phase mixing. There is no.
Why a higher order mode always so dominant?
That's a good question. Well, I think that has to do with the fact. Well, it depends on your perturbation. It depends on your perturber potential. And I have seen this that for the satellite galaxy, your phi p is such that the Fourier coefficients of that perturber potential for the higher order modes are going to be smaller. And that's why you get, I think that's a mathematical answer. Yeah.
So I'm staring at this release for way too long, probably. And what is kind of striking to me is that this time scale for you to go from something that's just kind of divided in half to having kind of almost 2 loops is not that much more than just 1 or 2 rotations, which seems kind of fast to me. And then I'm remembering that on Tuesday at our colloquium, our speaker said that we've only had, on the order of, I think it was 50 rotations in our galaxy. So can we combine these two to make any sort of, quantitative statement about when this mechanism might have started in our galaxy? Like, scale since this started might have been, like, can we,
yes.
Do we know that?
I think so. So first of all, there is no rotation of the galaxy in this case. This is not the movie. This is for a plain infinite isothermal slab with just a vertical profile. Isothermal in the vertical direction. And this is just a vertical motion. So the stars are going to oscillate in the vertical direction. And this rotation in the phase space is nothing but oscillation in the actual space, in the physical space.
Okay. So this wouldn't necessarily be able to be translated to the actual spiral arms that we see in the galaxy.
No, this is not a spiral arm. Okay, I'm sorry.
Okay, sorry. I don't work in this field, so sorry.
No, that's fine. Yeah. This is a phase space spiral. This is a spiral feature in the phase space, velocity versus position. And the spiral, now this might correspond to a spiral arm globally, but that is a different spiral that's in the physical space. Okay. And this is a phase space spiral. So this oscillation frequencies of the star, the vertical oscillation frequencies, those are what basically determine at what rate this phase spiral is going to wrap.
Okay.
It has nothing to do with the rotation in physical space of the stars.
But in our the spiral gives you a date for the impulse that caused it.
This spiral or the actual? The spiral?
In our stellar neighborhood, the phase space pattern evolves at a rate we know because we know the oscillation frequencies up and down. And so you can date the time when that perturbation was produced. Right? Yes. Right. And so what's the date? We don't know.
So are you asking that how does that compare to the estimate of the perturbation time from this
when
one?
did Sagittarius hit?
Yeah.
Right.
When did right.
So whatever.
Is 1 gig?
I think it's 1 gig a year, 900 mega a year, 1 gig a year. That's
I think it's a little shorter, maybe 300 to 500 million years.
Yeah, it depends on the
So have we made a full rotation since then?
200 megayears, yes, we have.
How many?
1.5-ish, I guess.
Okay.
And is the observed spiral m equals 1 or m equals 2?
Could we?
I mean the azimuthal mode.
The m in the vertical phase space, yes.
In the vertical phase space?
Yeah.
Oh, okay. Yeah, it's an n equals 1 mode. In the observed spiral is a 1-arm phase. It's n equals 1. Yes, I'm going to come back to that. Yes. It's a very important point. Okay. So we again come back to our favorite linear perturbation theory for collisionless systems. We perturb the collisionless Boltzmann equation, introduce a perturber potential, and look at the linear response of the system, how that evolves over time.
Sorry, I have a question about practically. So for the last slide, so if you just make a measurement of the Z position and the speed of stuff, are you not measuring something local in here?
Yes, I am measuring.
But like if we look out near us, you're measuring something. So then how do you determine the overall structure?
You cannot from this point. This is a very local picture. You sit at one patch on the disk and just sample the vertical positions and velocities in that patch. This is local picture. This does not consist of the entire global distribution of stars.
Right. But if I understand that. But if I just look out, I don't know how far we can look out.
Kiloparsons.
Okay. So if you look out that far, you can still measure. You can still get a sense of.
That's right.
Okay.
I think you can now with Gaia 3. I think you can go out to 1 or 2 kiloparsecs. You can go further in. That I know for sure. You can look what happens at 5 kiloparsecs.
And the idea then would be that if I were to measure this phase-space distribution at positions all across the Milky Way, there's some like different scale.
That's right. Yes. So how the phase of these individual phase-space spirals across the disk compare to each other. From that, you can get a sense of the global perturbation that nature of the perturbation that has caused in space. Okay. All right. So perturber potential creates linear response. Yes.
Sorry.
Okay. Now, the way we do that is by going, so we have the linear collisionless Boltzmann equation to solve. Go to the actionable space because your unperturbed distribution function and Hamiltonian are just functions of actions. So this simplifies the calculations a lot. And you do a Fourier series expansion in the angles, discrete Fourier series because you're of it's a discrete Fourier series because your perturbations are going to be periodic in the angles. And so you write down an expression for the Fourier coefficient, how that evolves as a function of time. F1L is the Fourier coefficient of the linear response of the system, and phi L is the Fourier coefficient of the perturber. And this is a very easy equation to solve. You can solve this using Green's function or any other favorite technique. And you get an expression for the closed integral form for the linear response once you specify how the perturber potential is going to change over time. So this is a key thing here. This and the frequencies of the stars, those are also going to. So basically phase mixing comes from this term in here. Different frequencies, omega 1, omega 2, omega 3. So you're basically, it's like a forced oscillator. You're forcing already the stars are going to oscillate at the natural frequencies. And on top of that, you're forcing it with some kind of perturbation externally. And now you're going to evolve over time, depending on how the perturbation frequency compares to the natural frequencies, you'll get a resonance or not. That's how it happens. And also the key thing is that you have this gradient in the distribution function with respect to the actions. So if you have a homogeneous system, you do not respond at all. you need to have some density profile. You need to have some kind of gradient in the distributed function. Otherwise, it will just go back and forth and everything is just washed out. So you need to have this gradient in order to have a linear response. Any kind of response, not only linear. And this perturber can be anything. It can be a bar or a spiral arm or a satellite galaxy moving through the disk. So here I'm going to focus on a plumber sphere moving through the disk at a certain velocity Vp in a straight orbit. It's ideal case, but satellite encounters that are highly eccentric in nature are going to look like this, not really a straight orbit. So even this thing is very hard to plan. Right. So I'm not going to show you the details of how the expression for the satellite encounter looks like. It looks horrible, but I'm just going to show you a plot of this bending mode response, the n=1 mode. So it's the 1 hour phase space spiral. How does the amplitude of that phase spiral look like for different satellites of the Milky Way? Sagittarius in the red dots. This is LMC, Hercules, Leo2, and many other satellites. I've done this for dozens of satellites. But these are the ones which create the strongest response in the solar neighborhood. And this is plotted as a function of the crossing time when these satellites cross the disk. Sagittarius had its last pericentric passage, which corresponds to a disk crossing time of around 900 mega a year in this particular case. But as Scott was saying, it can be shorter. If you change your potential a little bit, I've seen that that comes down to 500, 600 mega or so. And well, the upshot of this plot from the upper panel is that Sagittarius dominates over the others by at least 1 to 2 orders of magnitude.
The observed response, right?
Or Sagittarius?
Just for the observed.
That is, I think, 0.1-ish, 10% density contrast.
So in the region of Sagittarius.
Yes, yeah.
Sorry, another probably naive question. So can we use the phase space information from Gaia to understand what happened before the last, like, I would say, major encounter that would have started out these spiral arms? Like, do we know what the galaxy might have looked like? Like, did we have other spirals or not? Or does it kind of wipe out that information when you have
Yeah. I think it will wipe out the information if the, well, first of all, if the perturbation is strong enough, it wipe it out. But
So
also,
when we're looking at all of these, are all the ones that you're showing us essentially since, like, what was the thing, the Sagittarius encounter? Are these all since then? That would be like our biggest encounter in the last however many years.
well, these are shown at the times when the impact is happening. This is not the current day. The current day amplitude will have probably damped away because of many reasons. It can be landau damping, all sorts of things. This is when the Sagittarius crossed the disk 900 mega years ago. What is the response at that time?
Okay.
And similarly for all these satellite galaxies, what is the response when they cross the disk? What is the response today from that crossing? I haven't done that calculation.
Some of them will have across the disk since Sagittarius, but if they're puny,
Well, I guess what I'm trying to figure out is that still included in the Gaia data or not? Or I guess what you're saying is it's much less. It would be like
I think it is much less. At least this calculation suggests that okay, maybe the LMC has done some things, but not to the stars that are confined to the disk. Only the stars in the thick disk are going to be affected more by the LMC.
Thank you.
Right. But Sagittarius is probably the dominant among these satellite galaxies to have caused the Gaia phase spiral. Now that doesn't say that, I don't mean to say that Sagittarius caused the Gaia phase spiral. That could have been caused by many other things. Maybe the bar of the Milky Way buckled. There was some anti-symmetric perturbation. Some other satellite galaxy or of unknown, I don't know, it's like some darkness of halo, which is invisible, and that's passing by, and that might. Because there have been works in model simulations which claim that you cannot get the fine structure of the phase spiral and the bending, the actual how the VZ goes as a function of basically the asymmetry and the fine structure from just from the Sagittarius margin. There has to be something else which is also needed to account for all the structure.
Okay.
So it is.
So there's something, but it's hard to predict the details of that.
Yes.
Is that fair?
Yeah, I think so.
Thank you.
But the Sagittarius did pass through the disk. So it must have caused something. And we find that the solar neighborhood Sagittarius response is huge. So, of course, yeah. It's still, I think, an unresolved issue. What actually caused it?
It's kind of wonder, is there any possible orbit where you can, for which you can create a larger breathing?
That's right. Yeah,
more independent.
Yes, I think you can.
The inclination is very small.
Inclination. So this is for, so these inclinations are fixed from the data because so we have the current day phase space coordinates of all these satellites, and I time evolve them backwards in the full Milky Way potential, Milky Way disk plus halo plus pulse potential, and compute it at what angle, what inclination, and what velocity they cross the disk in the past. And from that, I use linear perturbation theory to compute the response. Now, that being said, if they had crossed at some other inclination, for example, I don't think I have that plot, but
that's right. It's just theoretically.
Yeah, theoretically, you can have different inclinations, and more parallel encounters actually cause more stronger bending modes. More perpendicular encounters cause stronger bending modes. I think that's how it works. And also velocities matter. If your impact velocity is large enough, you cause bending mode. If it is small, it causes bending mode. That's because it's actually not very hard to imagine, because let's say that there's the disk and the satellite is coming like that. And if it's slowly coming, then the disk responds like that. It goes up. And the stars towards the apocenter and the pericenter are going to lose. Stars towards the pericenter are going to gain energy, and the stars towards the apocenter are going to lose energy. So basically, the stars are going to move up. And when the satellite passes, the stars are going to go down, and the opposite thing happens in the neighborhood. So it's like an antisymmetric perturbation. But if it's going very fast, then it's like a symmetric. So you get a big.
I have a nice question. You say you take current position and so on and evolve backwards. How confident? Is that likely to be accurate or inaccurate?
It is probably not that bad up to maybe 1 gigayear in the past. We don't know for sure, but beyond 1 gigayear, I mean, the Milky Way potential has been changing, and it's been growing, it's accreting mass, and beyond 1 gigayear, I don't believe this, for example, this line, this point, no. Sagittarius, probably it's okay. Although, yeah, I would say I'm fairly confident about anything within 1 year. Although that needs to be checked with the time evolving potential of the Milky Way and everything. Okay. I don't think I have time to discuss this. But all right. I'm going to talk a little bit about perturbation of spherical halos and spherical galaxies, and how that causes dynamical friction, a massive perturber moving in a circular orbit. So why do we study dynamical friction? It's one of the key relaxation mechanisms in collisionless systems. You perturb the perturber system, and it responds to the perturbation. And the back reaction of that response on the perturber is basically dynamic. So that's how your massive perturbers perturb your galaxy, and the torque due to that perturbation on the perturber is going to gain angular momentum and energy, and it's going to spiral. And that's how we get galaxy mergers. We have the initial phase of binary black hole mergers, for example. We need dynamical friction for the black holes to come close to each other so that gravitational wave can take over. So dynamical friction is super important for all these different kinds of encounters. So the standard Chandrasekhar picture, which is the most popular picture of dynamical friction today, given by Chandrasekhar in 1943, It was a simple case of a massive perturber moving with a in a straight orbit with uniform velocity. And the stars are also going to move at nearly straight orbits. And they feel the gravity of the perturber, get deflected from their orbits, kind of form an overdensity or a wave behind the perturber. And this moment of exchange basically gives momentum, forward momentum to the stars, but drains the forward momentum from the perturber. So it gives a backward velocity push to the perturber. There are also going to be stars coming from the backward direction, which is going to do the opposite, but you have an asymmetry because of the velocity of the perturber. You will have more stars coming from the front than from the back, and therefore you have a net energy drain from the perturber. That's the drag force, the friction force, which is given by this famous Chandrasekhar formula. But there are approximations to assume that it's a homogeneous background of stars. There is no density profile in the background. And you also assume that the stars are moving around nearly straight orbit. So it's a fairly local picture. Now, yeah. And Scott Tremaine here and Martin Weinberg came up with this very ingenious idea of how dynamical friction operates in a more general kind of picture where in the real universe stuff is going in orbits and it's a self-gravitating system, so all the stars are moving with particular frequencies, and their orbits are not straight, as you see some Chandrasekhar, they're moving in curved orbits, which are characterized by tons of quantities called actions and corresponding frequencies of oscillation. Around the orbital plane, you have this round and round motion and the in and out motion, and those are the frequencies that are important. And the perturber is going in a circular orbit in this picture. Simple, not that simple, but still simpler than a general orbit. I mean, a general orbit of the perturber will be eccentric, but that is a different calculation. But for the circular orbit, you basically, whenever you have a resonance between these frequencies of the stars and the circular frequency of the perturber, those are the stars that are going to respond the most because they are going to be in sync with the perturber all the time. They're going to see the perturber again and again. And that creates a response density, which lags behind the perturber, and therefore it exerts a torque on the perturber. And that torque is basically known as LBK torque, which has a non-zero contribution only from the resonant stars. This was first provided by Lyndon Van Alkanash in 1972 in the context of angular momentum transport due to spiral arms in its galaxies. Tremaine and Weinberg generalized this to the case of dynamical friction in our spherical galaxy. The physics is the same. So both these theories, Chandrasekhar and the LBK resonance theory, have been found to work very well in cuspy galaxies. If your galaxy has a density cusp towards the center, then you find basically that dynamical friction is very efficient in driving the massive perturbers to the center, all the way to the center of those. But it has been found in many unbounded simulations over a decade or so that if you have a core galaxy, none of these standard pictures actually work very well. Chandrasekhar predicts that it fall all the way in, but, and this is a line from the simulation, this actually shows that initially it falls in at the Chandrasekhar rate, but then it speeds up. This is called super Chandrasekhar friction. And then it kind of hits a wall and bounces back. And there's like opposite of dynamical friction. This is what they call dynamical buoyancy. So this is Reed et al. 2006. And after buoyancy, it basically now undergoes some oscillations about a particular radius. And this is near the core radius. And this is basically where the perturber stalls. So it does not want to go further into the core. There's some kind of phenomenon which is happening that is trying to arrest this fall. So there is probably this dynamical buoyancy is countering dynamical friction. Something is happening here. And Cole et al. 2012 actually finds that if you now place the perturber very close to the center of the core galaxy, they were looking at globular clusters of Fornax galaxy, and one of the globular clusters in Fornax is at least the projected distance is very close to the center. And they find that that globular cluster actually gets pushed out instead of falling into the center. Dynamical buoyancy is found in N1 simulations. Now, whether that's robust or not, we were after that. We wanted to come up with a general theory that can predict core stalling, dynamical buoyancy, all these different aspects of perturbative dynamics in core galaxies, and come up with a theory beyond the standard theory we can predict.
For the cusp, does this is the dynamical friction is it robust for the slope being different, like r to the -3 or r to the -4?
think so. The outer profile does not matter much, but the inner, right. So the inner R⁻⁻1 cusp, for example, it has, I think, this calculation. I'm aware of calculation for isothermal sphere, but just R⁻², it works very well for that. And for an NFW cusp as well, I think it works very well. The LBK theory is for R to the 0. For R to the 0, the core, it does not work. Standard theory does fails there.
You're about 10 minutes.
Yeah. Yes, I'm not going to go into the details of this. So basically, this is linear perturbation theory all over again. Instead of the Hamiltonian, now you have the Jacobian Hamiltonian because your energy and angular momentum are not conserved in this case. If the perturber is moving in a circular orbit. So you calculate the linear response, get the torque. And now in the standard theory, you have approximations. First of all, you assume that the perturber grows very slowly. And you also assume that the perturber is infalling, inspired very slowly. So those are the two assumptions in standard theory, slow growth and slow infall, which I'm going to relax in my general theory. So with these two approximations, you get this LBK torque in the standard theory, which comes from only the resonant orbits. That's because the perturber takes infinitely long to present itself because of the slow growth and slow infall assumption. And therefore, in that time, all the near-resonant orbits of resonant orbits are phase mixed. So the only response is from that. And it is always retarding because it goes linearly with delta del E, which is negative for all stable systems. And therefore, you only get friction from LBK torque. There is no possibility for dynamical buoyancy. So if you evolve the perturber under the Sunseeker torque, it goes all the way in. LBK torque, however, predicts that you can't stall in the core. So core stalling is predicted by LBK torque, but dynamical buoyancy is not predicted. Now, why does it stall? That's because of a suppression of core rotation resonances in the core. And I'm going to come back to that. So no dynamical buoyancy, nor any superchancellical friction in LBK torque. So LBK torque, again, let me remind you, it comes only from the resonances because of its direct as a function of the resonant frequency. Now, when you relax the adiabatic approximation, you introduce the perturber suddenly instead of growing it very slowly over time. That's the opposite extreme that you can pick up. And you basically get these transient oscillations in the top from the near resonant orbits. But the phase makes away over time, and therefore in the time asymptotic limit, all you're left with are the resonance. But the perturber does not have infinite time. It is falling in, and therefore you never actually go to the LBK torque strictly. But you are always going to have some contribution from the near resonant orbits. But now the key approximation is the secular approximation. We relax that. We do not assume that it falls in slowly under dynamical friction. By slowly, I mean slower than the typical orbital time of dynamical time. Then this becomes a temporal correlation between the perturber potential currently when I'm measuring the torque with the perturber potential at all past times. This is integrated over the trajectory of the perturber. So this is like a memory effect. So the torque now depends not only on the current position and time, it depends on the entire history of it. And the frequency of the perturber is also going to change. So the resonances, there is no strict resonances in this picture. Near resonant orbits are going to dominate the torque, but the perturber is actually moving through these resonant orbits. The same set of stars are not in resonance all the time. And the perturber is, this is known as sweeping through the resonances, which is discussed in Strayman and Weinberg in the context of dynamical friction is slow rigid. So we have this thing, we have this orthodox looking expression in the torque, and therefore we need to solve this integral differential equation. This is a time integral here on the right hand side, and this is derivative, and this is hard to solve. So we did an approximation to solve it and to gain some insight as to what is the prediction of this theory without going into the detail of solving this with all its complexity. We assume that dRdt is nearly constant. Now this time dependence, this time dependence in the perturber potential comes through the radius because the perturber is moving in, and that is the time dependence. because the perturber is also going around and round, but this is done in the photoelectric frame, so that thing has been subtracted off. It's going round and round and falling in, and that in spiral is basically the Planetary Dynamics. So upon expanding this, we can do a Taylor expansion. If we assume that dRdt is constant, then we get that the total torque, self-consistent torque, is basically the instantaneous torque, which goes to the LBK torque. That is this instantaneous torque. This goes as sine of LK omega KT by LK omega. And this goes to delta of LK omega K in large time. So that's because of phase mixing in the near-resonant orbits. But there is this new term called, which we call the memory torque, which comes from this, the fact that the perturber is moving in. And this is proportional to dRdt, the rate at which the perturber is moving in. And this acts like feedback because the torque goes as dRdt, it's dLdt, so it goes as dLdR and this also goes as dRdt. So if this term, which is like a momentum, depends on the details of the orbits and the perturber, but you don't have to go into the details of this. But the key thing is that if it is positive, if this term is positive and dRdt is negative, then it causes a more negative term. And that basically gives acts like a feedback loop. And if this momentum like term is positive, then you have a destabilizing feedback. If you have negative dRdt, it tries to make it more negative. It falls in very fast. This is similar to what Riemann and Weinberg have in their paper. They also call this destabilizing and stabilizing feedback, but that's because of the change in the frequency of the perturber as it is falling in. But this happens to be change in the perturber potential. So that's the difference. Now, if you arrange these terms, your dRdt becomes this LBK torque divided by dLdr minus this momentum like term. Initially, this is 0 because there has not been enough memory. The perturber just started falling in, but it grows over time and tries to make the denominator smaller and smaller. So it basically falls in much faster than the LBK torque after some time. So that's how you get supercharged friction. And then at some point, this is going to flip side. And this becomes negative. This is already negative. So negative is positive. So you get dynamical buoyancy. So this particular radius at which dLdr is equal, so this is like the orbital momentum of the perturber, is equal to the momentum corresponding to the in spiral of the perturber. When these two balance each other, we have core stalling in this perturber picture. And therefore, this core stalling radius is like a stable limit cycle, because stuff that is inside is going to move out towards the radius, and stuff that is outside is going to move in towards the radius. And limit cycles are actually forbidden when the Hamiltonian is conserved. But in this case, the energy of the perturber is decreasing with time. So you have a dissipative system. So you can have limit cycles, and not only saddles and centers as you have in Hamiltonian. So core stalling radius is a stable limit cycle. So the orbital evolution basically looks like this. It gets faster and faster, and then plays sine inside a particular radius and stalls it. And if you're inside, then Chandrasekhar and LBK torque basically do not go out, but that's a consistent torque predicts that after some transient oscillation, moves out to that rate. So the dynamical buoyancy and super Chandrasekhar friction installing a robust predictions of linear perturbation. But there are caveats in perturbation theory. I cannot go into too much detail here, but basically, your perturber is not very weak in the core. The core of the galaxy does not have enough mass. The perturber is very massive. So core stalling actually has been found to happen when the mass of the perturber is comparable to the mass of the galaxy. So you cannot use linear perturbation theory all the way in. So everything that I've showed you is subject to question. Therefore, we move to a more non-perturbative approach, where we basically numerically integrate the orbits of the stars, considering restricted three-body problem in the combined potential of the galaxy and the perturber. And I'm showing you just one particular orbit here, It's called a horseshoe orbit. It's very well known in planetary dynamics, for example. This is a star which is moving in the combined potential of the galaxy and the perturber. And there's the co-rotating frame, there's the inertia frame. This is the energy of the star as it changes over time as the star is going around. And initially it's inside, then it feels the perturber's gravity, moves outside, and takes a very long time to drift in the co-rotating frame. It has a very long libration time because it's very nearly co-rotation resonant. And it spends a lot of time in the outskirts, outside the radius of the perturber, and then it again moves back in. And when that happens, its energy is going to change back and forth. So you have this periodic, nearly periodic orbit. So how do we get dynamical friction? It's a time asymmetric thing. So how do we get an asymmetry from a symmetric looking object? That's because there is a distribution function gradient along this orbit. Not all stars are going to do the same thing. There will be more stars in the inner part than in the outer part. So that the more stars are going to gain energy by moving from inner part to the outer part than the stars that are going to lose energy by moving from outer to inner. So there is a net gain of energy of all stars because of this distribution function gradient or density profile. And so overall, the perturber is going to lose energy there. That's how you get dynamical friction from this partial orbit. Now there are other orbital families. There's something called a Bachmann orbit, which is exclusive to a core galaxy. We identified this orbit for the first time. This looks similar to the horseshoe, but instead of taking a detour all the way about L0, it basically takes a shortcut between L1 and the perturber. And this only occurs in a core galaxy, it does not occur in a cosmos. The key feature is that all of these orbits take a very long time to vibrate in the co-rotating frame. So you can get a coherent response from these orbits. If the orbit was going like this, then everything would have been washed away and you would not get any coherent dynamical friction torque on that orbit. So these very nearly co-rotation resonant orbits are the dominant contributors to dynamical friction. There's a tadpole orbit which goes around the L4 and L5 Lagrange point. This is also very well known in planetary dynamics. So we have all these different orbital families. We have the horseshoes shown in the blue region. The red region is the tadpoles. The green region is the Bachmanns. And there are other orbits like center-filling and perturber-filling, which go around the galactic center or around the perturber very fast, so they do not do anything to dynamical friction. And the tadpoles, horseshoes, and Bachmanns contribute to dynamical friction. Outside the core, when this is for a Plummer sphere, the Plummer core for the galaxy, when the perturber is outside the core, then we have all these different kinds of orbital families, tadpoles, horseshoes, and Bachmanns. But the horseshoes disappear when the perturber enters the core. And only the Bachmanns are going to be the ones that are dominant inside. That's because there's a very interesting thing that happens because the galaxy is the core, the perturber is very massive and it tidally disrupts the core when it moves in. And it's called Roche lobe overflow. So basically the Roche lobe of this galaxy is being disrupted by the perturber. And what that means for the Lagrange points, these are the fixed points in the co-rotating frame, those undergo a bifurcation here. So your L3, L0, and L1 Lagrange points are bifurcated, merge together, and form an unstable L0. And previously L0, which is a galactic center, that was a stable fixed point, it's a core, but it becomes unstable once the perturber falls in. And this bifurcation of Lagrange points happens only in a core and not in a cusp.
Inside the core, like, do you not expect it to be like this? Rather, I mean, at least in it's like a bigger galaxy than spheres, like what you was in.
There will be
like Milky Way, I think like 10 kiloparsecs. I mean, you expect this contribution to be larger than.
That's right. Yes. But the disk is like a few kiloparsecs. Let's say the Milky Way. 30 kiloparsecs, and the galaxy, the Milky Way halo, it's like 200 kiloparsecs in period radius, and the scale radius will be like 20 kiloparsecs or so.
This effect comes into account only.
This effect comes when it is. That is true, but if the disk is like that and the halo is like that, so if the perturber is coming in like that, then I don't think the disk matters much. But if the perturber is coming in like that along the disk, then the disk will probably contribute to the dynamical friction torque. Yes. Yeah. I haven't taken the disk into account. That is more difficult, but can be done. Great. So how do we get dynamical friction outside the core? As I was saying, more particles here than here, and therefore you get a retarding torque. That's how you get a friction from the particle. But for a Backlund orbit inside the core, you have more particles here and here because the perturber is dominating the core. So the energy is highly negative near the perturber. And the distribution function is a decreasing function of energy. So more negative energy has higher number of particles. So there initially, in the equilibrium, there will be more particles here and here. And now due to libration of this orbit, because the perturber is moving that way, so the orbit will orbit that way. And therefore, an overdensity actually initially develops ahead of the perturber inside the core rather than behind. And therefore, you have this enhancing torque, which tries to pull the perturber outwards. And it tries to increase its angular momentum, push it outwards. So that's how you get dynamical buoyancy before friction sets in. And this initial enhancing torque is going to push the perturber out. And then now this process is going to continue and you won't ever get to this friction. So now this bifurcation of Lagrange points, you can derive a correct, so this is a bifurcation diagram, radius versus x, which is a line joining the galactic center to the perturber. You see that the Lagrange points marked here, but do not in the cusp. And you can get a criterion for bifurcation radius. You can basically calculate analytically what is the radius at which this bifurcation happens for a given density profile of the galaxy and a given mass ratio of the perturber to the boson. And that's that's basically this line. That's analytical calculation. So when bifurcation happens, horseshoe orbits disappear and the Backlund orbits dominant. And near the bifurcation radius, the libration time of the Backlund orbits actually goes to infinity because bifurcation means that things are slowing down. The Lagrange, the libration time about the N0 Lagrange point is actually going to infinity. And therefore, it takes very long for the response density to develop along these Backlund orbits, which dominate in the core, and therefore it takes very long for the dynamical friction to operate. And that's why core stalling is actually happening when the bifurcation happens. Okay. Now I don't want to explain more, but yeah, this is one slide which I had about. This is about astrophysical implications of buoyancy and core stalling. Why is it important? So we have found that dynamical buoyancy and core stalling are probably robust predictions of dynamics. It's not an artifact of n-body simulations, but it is probably there. And that means that it will probably operate in the real universe as well. And for example, it can choke supermassive black hole mergers in core galaxies. If a black hole is sitting in the center and a black hole is going like that, it won't be able to go all the way in to the core because of this core stalling. And globular clusters can also stall. For example, in dwarf galaxies like fornax, it has been argued by many papers that maybe fornax has a dark matter core because many of these globular clusters, we can see that they're floating around, whereas from the Knight-Jones-Secker formula, for example, you estimate that these globular clusters should have decayed all the way to the center, but that hasn't happened, and therefore maybe there is a dark matter core which is causing this core stalling, and so that's how we get these globular clusters in the outskirts of fornax. And yeah, so off-center perturbers are a robust prediction of dynamical buoyancy and core stalling. So if you look at galaxies are dark matter dominated, then central objects, if there are central nucleus star clusters or supermassive black holes, then that would disfavor the dark matter core. Because for a dark matter core to be there, you must have core stalling and dynamical buoyancy. So all these massive perturbers should actually be slightly offset. But if there is no offset, then the dark matter probably has a cusp and not a core. So that's one prediction. Then you can also try to predict what is the nature of this dark matter core. Is it a CDM core or a fuzzy dark matter? That's because the bifurcation radius, which is so all that everything that I've shown you is valid for collisionless systems. So CDM and stellar galaxies, stellar systems like galaxies. So for a CDM, the bifurcation radius is an increasing function of the mass ratio. More massive perturbers stall further out because more massive perturber ideally disrupts the core earlier. And that's why your bifurcation radius is, so the offset radius rather, is an increasing function of the mass ratio. But in fuzzy dark matter, it has been shown by papers like Barod et al. 2019 that more massive perturber is actually able to penetrate further into the core. So your offset radius is going to be a decreasing function of the mass ratio. And therefore, if you have observations of these offsets of massive perturbers from the centers of galaxies, if you plot the offset radius as a function of the perturber to host mass ratio, if it is increasing, it probably favors a cold dark matter core. If it's decreasing, it probably favors a fuzzy dark matter core. So that's how you might want to constrain maybe nature of dark matter using this buoyancy integration. Okay, so yeah, yes, I think yeah, this is I am trying to talk about this one. Yeah, summary slides. Thank you.